So in this last section of Chapter 5, we're going to be looking at solving equations using factoring. And the idea here is, up to this point, any equation we've solved has been what we call a linear equation. Ever since Chapter 2, the process of solving these equations is the idea of getting x, or the variable, by itself. However, now that we're working with polynomials, if we were to see a polynomial of any kind like this show up within an equation, it's no longer that simple. There's no simple way of just moving terms or multiplying or dividing to end up with an x on one side and a number on the other, like we've been doing for linear equations, right? We need a new approach is the issue here. And really, it's as soon as you see this x squared, or your variable to any power at all, really, that is what no longer makes it a linear equation and requires a new approach. Now, our new approach is really based on one simple idea. It's right here, something we call the zero factor property. And this is just a version of it, or simplified version of it. It says if AB equals 0, meaning if A times B, if two things multiplied together give you 0, then A is 0 or B is 0. And this rule, this idea, is only going to apply to the number 0. The idea that if two things multiply to give you 0, one of them has to be a 0, right? That wouldn't make sense for, say, the number 4, right? If I say two numbers multiply to give you a 4, it's not the case that one of them needs to be a 4. It could be 2 times 2, right? But for 0, one of them, or both of them, could be the 0. Either 0 times b or a times 0 would give you 0 as a result. This also works for more than two things. If it's a times b times c, same idea. But that little idea there is what we're going to use to our advantage, along with the idea of factoring, which, remember, factoring just means writing something as a product, as a multiplication. So all we're going to do is what this mixed trick highlights here. We're going to get an equation to make sure it says stuff on one side equal to 0, then factor, and we'll talk about this step here. And in fact, we're going to kind of go backwards with this process. Notice, for our first example, if we look at what's on the left-hand side here, this is already in a factored form, something times something. In fact, that looks like a factored form we would have seen earlier in Chapter 5. And notice it is set equal to 0, so we basically have 1 and 2 done. So what does this third line mean of set each factor equal to 0? That is where we're using this property. We're utilizing the zero factor property because right here we have something times something equals 0, and what that's telling us is then it must be true that either x plus 2 equals 0 or x minus 3 equals 0. It's us using this idea right here. Two things multiply to 0, one or the other must be a 0. But by doing that, you've taken what was one equation and broken it into two equations, but each of those equations is a linear equation, right? Simply subtract the 2 over or add the 3 over, and you get two different solutions, two different answers, which is something else we've not seen before, an equation with more than one solution. But either of these works. If you plug in a negative 2 here and here, you'll get 0 times a negative 5. Well, that's 0. If you plug in 3 here and here, you'll get 5 times a 0, 0. So they both work. So our solution set, our set of possible answers, is both of them. That's a negative 2 and a 3. Those are supposed to be braces. For our solution set, those are both answers for x. And so that is what this set each factor equal to 0 step is referring to. Over to the second example, you'll notice we already have it equal to 0. We have step 1. But this now looks like something we can factor. This is an x squared x no x, so it's our quadratic. It's got a 1 out front, so it's our easy case. We're still going to think of GCFs always, but GCF of 1 here doesn't help us. And now we're just doing the easy case number game. Numbers that multiply to negative 4, so 1 and 4 are 2 and 2, but they got to multiply to a negative 4 and add to a positive 3. So negative 1 and positive 4. And remember, for the easy case number game, we'll just start each of those binomials with x, throw the minus 1 and the plus 4 in there, and we've got our factored form. And again, now that it's factored, this times this equals 0 means either that's 0 or that's 0. So add the 1, subtract the 4, and we've got, again, two different solutions to that equation. All right, so on the next page, we'll be given an example here if it wants to focus, where we have an x squared in our equation, but at the moment it does not say equals 0, so we do not jump into factoring. We start by saying, let's move the 6, right? Add 6 to both sides to get it over to the other side so we can get that form. Now that looks like a form on the left-hand side that we can factor. So again, to factor it, GCF is 1, is another x squared x, no x, easy case. So numbers that multiply to 6, positive 6, but also add to a negative 5. That would be, there's our options, and it would have to be negative 2 and negative 3 to multiply to a positive 6, but add to a negative 5. And so, easy case again, starts off with x's, minus 2, minus 3. I'll keep mentioning, don't forget to write that equals 0, because some people get distracted by the factoring and then forget they're solving an equation, right? We're trying to get to answers for x here. So if you don't write that equals 0, you can forget to continue the problem, where we get our values for x of 2 and 3 for our final solutions. All right, number 4. Again, we don't see equals 0, so we'll move everything to one side. And we'll do that just by subtracting 7x on over. Now I've got equals 0. Now I want to factor. I want to start with GCF, and this is the place where GCF is crucial that you do it first, because it's actually really the only way to do it. These two terms have a GCF of x in common, so we will factor out that x, be left with x minus 7, and notice that's as much as we can and as much as we need to do, because what we have is something times something, but these are both linear factors. It doesn't quite look like the two binomials, but that's okay, it won't always. This GCF is in itself a linear term, and if I say this times this equals 0, it's still the case that either that GCF equals 0 or the x minus 7 equals 0. Now notice there, that's just an instant solution. That's saying x could be 0. And that makes sense. If you plug 0 back up here, that would be a 0 equals 0. Here is the only one that looks like our other ones we've been doing, where you add the 7 on over to get another solution of 7. So our solutions are 0 and 7. So it's important to point out that a GCF, if it involves a variable, does lead to a solution, right? It is something you had as a product here that could have given you a 0. Okay, number 5, same thing. We gotta get that equals 0. So first thing I'll do is subtract the 25 on over. Now to factor, the GCF is just a 1. And this, two terms, subtraction between them, those are both squares. This is a difference of squares. I'm going to go ahead and use that approach where I say, what is the a squared, what's the b squared? So what do you square to get x squared? X. What do you square to get 25? 5. And then we just remember our formula. Difference of squares factors to a plus b, a minus b. So x plus 5, x minus 5. And notice those are linear, so we're ready to split this apart. And then here we subtract 5, there we add 5, and we get our two solutions, negative 5 and positive 5. All right, over to the next one. We've got our equals 0. So, first step, GCF. There is a GCF, notice, 2, 10, and 12 all have a 2 in common. Let's factor out that 2. Drops that down to x squared minus 5x minus 6 equals 0. Now, this is our trinomial, x squared x no x, and because of the GCF being out front now, this is an easy case. So we can just look at the number game of negative 6. Numbers that multiply to a negative 6 but add to a negative 5 would be a positive 1 and a negative 6. So the GCF of 2 is still out front, but our easy case number game gives us x plus 1 and x minus 6 for the factors, okay? Now, in this case, we have a GCF, but the GCF is just a number, just the number 2, right? It does not involve x. So that's not going to lead us to a solution, right? We're only looking for solutions to our variable x. So in this case, it's just this linear factor and this linear factor that could be zeros to where we will create our equations from them. Notice it wouldn't even make sense to write this as 2 equals 0. That just doesn't make sense. But these we can solve for x and determine the values of x, which as I kind of mentioned, but I'll mention more directly here, all these answers we're getting, you can absolutely check your answers just with just like any equation you've ever solved. You're saying these are the numbers that make this equation true. Well, plug back -1, plug back 6, and make sure it does make the equation true, and then you know you've got the correct solutions. So never forget that you have that at your disposal as well, the ability to check. All right, and a couple more here. All right, next one, we see the equals 0. So first step, GCF. Looks like here we've got a 2 in common for the coefficients, and if you notice, there's an x in all 3 of those. So 2x will be our GCF. Factoring that out, we're left with 3x squared minus x minus 10 equals 0. Now this, x squared x no x, but with a 3 in front, this is going to be our bottoms up approach. So 3 times -10, that's our a times c, gives us -30, 1 and 30, 2 and 15, 3 and 10, and 5 and 6. I want the pair that multiplies to -30 but adds to a -1. That'll be a +5 and a -6. Now, remember, I'm going to just leave this 2x alone for the moment, but don't forget it. Remember, with the +5 and -6, we're going to think of it as x plus 5 and x minus 6, but then we're going to put each of those over that value of a. This is the next part of bottoms up. So the a is a divisor there. Now 5/3 doesn't reduce. I'll write him again. -6/3 reduces nicely to a -2, and then the bottoms up comes into play. So now we've got 3x plus 5 and x minus 2, and then I will bring down our GCF of 2x, and all of that is equal to 0. So we had to break for our bottoms up approach to get to this factored form. Now notice our GCF again involves x, so this will lead to a solution, as will each of these. Now in this case, when you divide both sides by 2, you still get x equals 0. Here, for the first time, we'll need to do 2 steps. We'll have to subtract the 5 and then divide by that 3, giving me -5/3. And then over here, just move the 2 over, but notice that gives us 0, -5/3, and 2, all as solutions. And so let's point out real quickly here, what we started with, for the first time here in this section, was an x cubed. So this power on your x, don't think of it as this is telling you how many solutions you'll have, but think of it as this is telling you the maximum number of solutions you'll have. So for all those other examples where we had x squared as our highest power, we were never going to get more than 2 solutions. Now there are examples where you'll get less than 2. Just like here, you could get less than 3, but you never have more than 3. In this case, we had exactly 3. All right, and the last one here, everything we want on one side, so let's move everything to the left-hand side. That's where my leading term currently is x cubed, which is positive, so I like that. I want my highest degree term to be positive normally. So I'll move the other 2 terms over here, subtracting 4x and adding 12. Now that's 4 terms. And other than the GCF of 1 not helping us, we would go into grouping at this point. So that's our factoring technique for 4 terms. First 2, always plus second 2. Now the GCF of those 2 terms is x squared, leaving me x minus 3. The GCF of those 2 terms would be a 4, but also because of that lead term being negative, we'll make it a -4. That becomes a positive x, and that becomes a -3. Now, with grouping, we needed that to happen. We need that big GCF in common. So x minus 3 can factor out as a GCF, and then x squared minus 4, right? The leftovers create our other factor. Now, the issue is we're not done because we do not have only linear factors yet. We need to keep going. This right here needs to break down further. Now, x squared minus 4, 2 terms with a subtraction, and those are both squares. So we're looking at another example of a difference of squares. The thing you square to get x squared is x. The thing you square to get a 4 is a 2. So you still have x minus 3 sitting out front there, but that breaks down with our difference of squares to x plus 2x minus 2. And so we again have 3 different linear equations that we can create by setting those factors equal to 0, giving us 3, -2, and +2, all as possible solutions to our equation.